My name is AJ, and I'll be your presenter for today. So ATAR notes, you guys have probably heard about them before, maybe. Um, and it's basically like an online forum. It started out as an online forum sometime in like 2000s, and then from there they've sort of like built on into providing a lot of free high school like resources for students just to even that playing field. And these lecture series are just one of those. We have things like obviously the forums. We have free videos on our website that help with certain topics, so on and things like that. So I graduated in 2021, so about 2 years ago, which is kind of weird. But yeah, 2 years. Um, and I got an ATAR of 99.15. And I am now studying a Bachelor of Philosophy at the Australian National Uni. Even though it does say philosophy, it's kind of weird. I'm just really only studying bio, and like chem, maths, that sort of stuff. But yeah. Alrighty, so just some quick things about Slido. You guys have already started asking questions, but I think this code or this QR code should be on your screen as well. But if not, use this and join in. On this, you can ask me any question about methods, really, um, and I'll try my best to answer them. If you see a question that you like, um, don't if you see a question that you want to ask as well, don't resend that question. All you can do is just like press the like button and it'll get pushed up, right? You can see, like the latest question has 6 likes, and the top question has 8 likes. So I'll probably be answering the top questions first and then moving down the list. So if you want to see a question answered sooner, just press the upvote button and it'll end up higher. We will have a designated like question time. But yeah, um, hopefully everyone is all good with that. I might actually start off with answering some simple questions. And about the bound reference, we do have some extra things in there, like in the slide at the start, I think, about bound reference. If not, I'll talk about that as well. So I'll just leave that here for now. Wow, there's a lot of questions rolling in. Um, so I think this one is a really good one that I really want to cover right before we get into the lectures. What is the best way to study for maths? And are there any strategies that work particularly well for you? Um, I think you've probably heard this before, but I feel like the best way to study for maths is just to practice. Maths is, it's a very logical sort of subject, but the way VCE does it is like there's only so many topics they can test you on and so many like specific question styles. So the more questions you do and the more you expose yourself to a variety of question types, the more prepared you'll be for your SACs and obviously your final exam. Um, Also, another thing that I do want to mention is that Methods 1, 2 has a heavy carryover to Methods 3, 4, especially all of this functions and, graphing and calculus stuff that you guys will learn. A lot of that carries over to 3, 4. So yeah, try remember like a decent amount of things from 1, 2 and take that into 3, 4. So don't slack off in 1, 2 just because, oh, it's just another 1, 2 subject. It doesn't really matter until 3, 4. Like that's not really the case with methods just because it carries over a lot. But yeah, hopefully that answered this. The one that particularly worked well for me was definitely practicing a lot. Another thing I did, and I talked about this a lot in the Methods 3, 4 lecture, I did a lot of like research on my own into like the background of the theorems that they were teaching us. So when graphing, there are like certain rules that you're just told, right? But then going further and actually questioning why is that true, you'll build your mathematical understanding to like a deeper level. And so whenever you get a weird question, you'll be a lot better equipped to tackle this question. So always ask why whenever someone gives you a theorem, right? Or like a statement. And the best way to find answers to your questions is probably YouTube, Google, yeah, anything like that. Like Stack Exchange, they have an insane amount of like resources online for this sort of stuff. Um, but yeah, hopefully that answers this. Just take that off. Also, I like this question here because it's sort of linked in with what I said earlier. Should you continue on with your 1, 2 reference book in 3, 4? I didn't do that because there is some overlap, but it's not 100% overlap. And I'll talk about this when we talk a little bit more about your tips for your bound reference, but your bound reference needs to be specialized for you, right? And you'll hear me say this a lot throughout the lecture, when it comes to study methods, or, making a bound reference, it needs to be really, really specific to you. Just because it works for, Joe doesn't mean it will work for you, right? So you want to make sure that your study methods, your bound references are catered for you. So the problem with having your 1-2 reference book in 3-4 is the other thing is you want to have your bound reference very concise. So then when you like flipping through your bound reference, it's easier to find bits of information. So I wouldn't recommend carrying on your 1-2 reference book in 3-4. I'd say restart it again. Because not only will they dump a load of like new content, some of it is changed. So I think probability might be a bit different in 3-4. So yeah, I wouldn't recommend continuing on with it. Um, what I did in 1-2 is that I had my like I had a reference book and I like wrote in that reference book. But in 3-4, I just typed up my bound reference. So yeah. Okay, folks. I'll get on with the rest of the questions at about question time. So that'll be about halfway. Maybe even like I'll give a shorter break just to answer more questions. Feel free to keep sending in more questions, because the more questions there are, the better the session will be. Because the maths is something you guys can learn on your own, really. But I think getting these questions answered is definitely invaluable. Okay, let's get on with the maths. If you guys have any questions, after the lecture, or even, during the lecture, or really anything, but you don't want to like, it might be like, a very personal question, whatever. Feel free to like email me at my email address here. I'll just turn the laser pointer on. Feel me like email me at my email address here. I love receiving emails from students, and it's even better, getting to help more people. So yeah, feel free to do that. Okay. Another thing I should mention is that this lecture is recorded, and so you can watch back at it. If there's a part where I go really fast, you can watch back at it in your own time, and pace yourself like that. Also, these slides are available on that website as well. And the last thing before we get on with it is that these slides aren't really designed for me to finish, because there's so much content, and obviously I can't cover everything, right? So it's a very brief, like sort of jump into every small topic, really. And if we don't finish it, the rest of it is for you as notes. You can read over it in your own time, and annotate it, add it to your bound reference, things like that. Alrighty. A bit more on ATAR notes resources. Like I said, articles. There's a cool ATAR calculator, but that's probably a bit more useful next year. We have the lectures, obviously, forums, newsletters, and videos, study notes, which are all really helpful, I think. On top of that, we also have our TuteSmart resources. So TuteSmart is a one-on-one online tutoring sort of program. We also have group classes that run weekly. And we have study guides, and we have Ed Unlimited, which is effectively like an online library of just study guides. So we have like a NEEP, we have ATAR notes, obviously, and we have a crap load of practice exams up there. So yeah, definitely go check it out. Alrighty, so today's game plan. So like I was saying before, there's a lot of carryover from Unit 1-2 to Unit 3-4. So there's a lot of topics today, and you can come back at any time because it's recorded and you have the slides. So I'm going to try to split it up into 2 content blocks. So have some content, a little bit of practice questions, and then a bit of Q&A, and then content again. We'll try have a 15 break in between, but we'll see how that goes. Again, ask questions in the box and upvote similar ones. Ask anything really. I'm happy to answer, a variety of questions. So topics we're covering today is linear geometry, quadratics, transformations, inverse functions, and probability. You guys may have already come across linear geometry and quadratics in year 10, but it might not have been like a very solid basis. So my goal today is to try to get you, a very solid like a starting ground when you guys get to year 11. And yeah, so you can be just slightly ahead of your peers. All right. Hopefully people know what linear geometry is. If not, that's perfectly fine. Linear geometry refers to straight lines, or a linear relation is a polynomial of degree 1. So what is a polynomial? A polynomial is when we have like x to the power something, x to the power 2, x to the power 3, x to the power 4. A linear relation is just something that's x to the power 1. So, you've definitely seen this before. Anything in the form y is equal to mx plus c. Um, and hopefully you have come across this before. You can see, that's to the power 1, right? That x there. So we say it's a polynomial of degree 1. The c tells us the y-intercept. The m tells us the gradient. And that's really all there is to know from this. All right. So now that we know, what is a linear line, well, what are some things we can do with the linear line? And one thing that's really nifty, and they do get you to do this in a lot of different questions, which can be annoying, is finding the distance between 2 points, right? So, given x1 here and x2 here and y1 and y2, how do I find the length of this line? I'll give you guys a bit of time to think about it. Maybe you guys can come to the solution yourself. Think a little bit about right squared or right angled triangles and how we can use that here. I'll give you guys maybe 30 seconds to have a think about that. Okie dokie. Well, hopefully you guys had to think about it. I think the best way to go about doing this, finding out how to do something, is to draw it out. Once you draw something out, it's really easy. Well, it makes it not really easy. It becomes a lot more easier to visualize things. You don't have to do everything in your head. That's another thing that's really important in maths. Don't be afraid to draw. You really want to draw out these scenarios because they give you really confusing scenarios, right? And you need to be able to like sort of piece together that information. Best way to do that, draw it. Alrighty. Let me see if I can get my pen out and we can try work this out. The reason I brought up a right angled triangle is because, well, we know Pythagoras theorem, right? A squared plus b squared is equal to c squared. And that's what we can sort of use here. So I'm going to make a line between these 2 points. Well, that's a really janky line. Assume that's a straight line. And then I'm going to make a line down this way here as well. Actually, I'll do it in a different color. And I'll do it in dots. Okay, cool. So now we have a right angled triangle here, right? Now, how do we find the lengths of these sides, right? How? Well, we can create a third point here. What's neat, right, about doing this is that we know the x coordinate of this point and we know the y coordinate of this point. So this point is just x2, comma, y1. Okay, cool. That's kind of nifty. Well, so how do we find the length of this line? If we're not changing, the height, and we're only changing our x position, to find the length of this line, we just need to subtract both the x coordinates. Ooh, wait, give me 1 sec. I think my laptop's about to die. That is not great. Yikes. All right, hopefully it's fine now. Okay, so as I was saying, since it's just the horizontal distance that's changing, what we can do is we can do x2 minus x1, and we'll find that distance here. So x2 minus x1. Cool. And we can do the same thing for the height. Since all that is changing is our height or our y position, what we can do here is subtract our y positions. So y2 minus y1. Okay, cool, right? Okay, and I'm going to call this side d, or distance. If you guys remember Pythagoras theorem, it's a squared plus b squared is equal to c squared, right? So I'm going to do x2 minus x1 squared plus y2 minus y1 squared is equal to d squared. Okay, and now it's our final step. We just need to solve for d, right? And the way we do that is we take the square root. So d is equal to, I'm just going to write this out again, x2 minus x1 squared plus y2 minus y1 squared. And the last step is we just take the square root of this. Cool, nice and easy, right? So that's actually our equation for the distance between 2 points. Yeah, sweet, cool. I think, yeah, I also had it already animated in here. So you guys can also see this again in your spare time with a cool animation in the middle as well. All right, so a couple notes on the distance formula. It's not on your formula sheet, so this is something that you will need to remember. And a good way to remember this is to just derive it using Pythagoras theorem, like we did just then. If you do ever forget it, you can just really rederive it again, but ideally you would never forget it. And when you're substituting points, it doesn't matter, which one is x1 and y1, which one is x2 and y2. It's because you're finding the difference between x values and you're finding the difference between y values. So you're finding like the absolute difference, right? Like the difference between 5 and 0 is the same as the difference between -5 and 0, right? Just because, to go from 0 to -5, I need to travel -5 steps back. It doesn't make it too different from going from 0 to 5 because all you need to do is travel 5 steps forward. Like really, it's like the direction that has changed, if that makes sense. Sorry. Yeah, that's really it. Okay, so how do we go from here to find the midpoint between 2 points? Well, we know how to do the distance. Would the midpoint be the same? I'll let you guys have to think about that. Here's the formula anyways. Sorry. Here's the formula anyways. Have a think about why we can't just take the distance and then half it. I'll give you guys a couple seconds to think about that as well. Okay, all right. So if we go back to the distance formula, you'll see that it doesn't give us the coordinates. It only gives us the total length of this line, right? However, to find the midpoint, we want to find the coordinates. So what we're doing here is taking the average of the x1 and x2 points and the average of the y2 and the y1 points. That's all that's happening here. That's just an average formula. And so the average of 2 points, or if you're taking the average of two things, you should generally land in the middle of those two things. So that's what we really use here. So by taking the average of these two, we're landing in the middle of it. And like so with y2 and y1 as well. Okay, let's talk a little bit about the gradient. If you remember, the gradient is represented as m in y is equal to mx plus c. So the gradient is usually referred to as rise of a run. Why, right? Why would it be rise of a run? I'll get to that in a little bit. And so that's one way people remember it, rise of a run. I like to think about it as change in y divided by the change in x, and that's just y2 minus y1 divided by x2 minus x1. Once you guys get to calculus, this statement might make a little bit more sense. That's why I like it a bit more, just because it's very descriptive of what calculus is. Okay. I'll let you guys have a crack at this. I'll give you guys about 30 seconds to do this. So have a go. And yeah. And don't be hesitant to draw it out if you need to. Okay, hopefully that was enough time. All right. Um, so our very first step is to substitute in what we want to say as x1 and y1. Again, this is arbitrary. It doesn't matter which one you set to be the ones and which one you set to be the twos. In this case, I've decided to set 3 as x1 and 2 as y1. So I just plug everything in, subtract everything. You'll notice that everything is happening in steps. And this is not just only to show you guys, you know, what every single step is, but it also helps me like know, like when I did my actual exam, this is how I did it. Some of you might be like, oh, you can just skip from this to -1, but I found it more helpful for me to take it step by step. It prevented me from making really silly mistakes. Like, sometimes I could do 1 minus 3 is -4 or something really dumb like that. So yeah, this really helped me prevent silly mistakes in the long run. So yeah, you can use this to find the gradient between any 2 points. And so that's why, we get that equation. So any 2 points that lie on, the same line will have the same gradient. Okay. Um, if we do this in a different order, we get the same values, right? So, we label this as the ones and we label this as the twos. We'll still get the same values. It doesn't matter what order you do it in, as long as your twos and ones are consistent. As long as it's always 2 minus 1, it's fine. Okay. So why is it rise over run? Well, this is our linear line, right? This is x1, y1. This is x2, y2. Oh, well, I guess this one is x1, y1, x2, y2. I'll get out my pen. So x1, y1. Sorry about the really bad handwriting. I'm drawing on a mouse pad, so x2, y2. Okay, cool. Um, Now we can, again, like before with the distance, we know that this point here, oh, that's not a minus, by the way, that's a comma. This point here, we know that this is going to be same x coordinate as x2, same y coordinate as y1. So really, the distance between this point here and this point here is just going to be x2 minus x1 and y2 minus y1. Okay, so now you guys can see rise over run is just y2 minus y1 divided by x2 minus x1. Another cool thing to note is that since we can form this triangle, we can also use tan. If you guys remember, tan is opposite over adjacent. And that gives us tan theta is equal to rise over run. So if we have a linear line, right? This is a common question type, by the way. If we have a line like this, and we want to know what this angle here is, but we can find the gradient, equate it to tan theta, and then do arctan theta. So arctan is just like inverse tan of the gradient. And that will give us, our answer there. All right. Have a go at doing this. I think the polls aren't working, but have a think, and I'll reveal the answer in a little bit. Alrighty. Okay, this is a bit of a throwback. Hopefully you guys remember some stuff from last year, maybe, if you were taught it. All right, so what is not a method for finding the x-intercept of a quadratic? Um, well, the quadratic formula, by definition, will tell us the x-intercepts. Completing the square is a form of factorization, which can lead to solving the x-intercepts. And null factor law is also how we figure out x-intercepts. If these terms aren't familiar to you, don't worry, we'll go through them soon. But the one way to not do it is to convert it to expanded form. It's really difficult from doing that. Um, so try not to ever do that. So if that's the only, like, if you don't understand what, the rest of these are, at least take this away with you. So then in the next couple slides, we can get into, how to do the rest. So then, the right way of finding the x-intercepts. All right. So on to polynomials. So this is something I talked about a little bit before. Polynomials are when we have something to the power of x, x to the power of something. So you can see, this is a quadratic. It's ax squared plus bx plus c. This is a cubic, y is equal to ax cubed plus bx squared plus cx plus d. And we have quartics, y is equal to ax to the power 4 plus bx cubed plus cx squared plus dx plus e. Okay. The only information that, that this expanded form tells us is the y-intercept. And that's because if I do, again, I'm just going to get my pen out, the y-intercept happens at x is equal to 0. If I do that, this will tell me that the y-intercept is equal to c. Here the y-intercept is equal to d, and here the y-intercept is equal to e. That's because when x is equal to 0, all of these terms here get cancelled out, because they're all 0 terms, right? Okay. Hopefully that's something that makes sense. All right, I'm going to move on from this form. Okay, factorized form. So factorized form is a lot easier to deal with. I think visually it also looks nicer just because everything is bunched together. So this will tell us what the x-intercept looks like. Though keep in mind that not all polynomials can be expressed in this form, and you'll definitely come across polynomials that you can't factorize, and with those it's a little bit harder. Generally, non-factorizable polynomials don't have x-intercepts. So that's a pretty good rule to keep in mind. And if a polynomial, yeah, so this is basically what I said. And also x-intercepts happen at y is equal to 0. So let's say the quadratic. I'm going to set y is equal to 0. And that's going to be equal to a times x plus b times x plus c. We can divide both sides by a, and so we'll get 0 is equal to x plus b times x plus c. Okay, how to think about how we would go from this into finding the x-intercepts. See if you can come up with any solution to this one. Again, I'll give you guys about 30 seconds to think of that. Okay, so hopefully you guys maybe could have come up with a method. If not, that's perfectly fine. This is a weird sort of rule. It's called null factor law. And that basically says if we have two numbers, let's say we have a and b, if we have two numbers that multiply together to get 0, either a or b is equal to 0. So a equals 0, or b is equal to 0. Which makes sense, right? If we have 4 times 0, well, one of those numbers is definitely 0. Any two numbers times 0, one of them always has to be 0. It doesn't even have to be two numbers. Any three numbers, any four numbers times 0, one of those four numbers has to be equal to 0. So that's what we're using here. So what we can say is either x plus b is equal to 0, or x plus c is equal to 0. And then from here, we can resolve for b and c. So our x-intercepts in the quadratic case would be x is equal to minus b, and x is equal to minus c. All right, so hopefully that makes sense for everyone. Okay, so let's talk a little bit about what the different forms of factorization are. So here you'll see that everything is to the power 1, right? But sometimes with quadratics, what we can have is a repeated factor. So in some cases we can have, or even with cubics, right? Sometimes we can have x plus a squared times x plus b, right? What does that mean? We have two of the same factors. Like, how do we deal with that? Um, whenever something is raised to some power, right? The type of intercept it is will change. If it's to like a linear power to the power 1, it's just going to cross the x-axis normally. If it's squared, it's going to become a turning point. It's going to like parabolically touch the line and move on like so. And if it's to the power 3, we'll get this weird, cool shape like this. And this is called a point of inflection. I'm going to write POI. Sometimes it's called stationary point of inflection. You'll probably come across that more in E11, but it's called stationary point of inflection, usually. That's when we have something to the power 3. You'll only really see that in cubics and quadratics. Okay. And one of the other forms, and probably the last form I think we're covering today, let me just check. Yeah, is stationary point form. So stationary point form of a polynomial is going to be sum plus c value and everything else in this squared or cubed or quadratic bracket. Again, not all polynomials can be expressed in this form. If they can't, they probably don't have a stationary point. Quadratics are always expressed, like can always be expressed. So for quadratics, this is going to be a turning point. For cubics, this is going to be, those point of inflections I was talking about earlier, this stationary point of inflection. And for quadratic, that's again going to be a turning point. Maybe some of you guys haven't seen a quadratic. I'll try pull up Desmos and see if I can get you guys a nice sort of image. If you haven't seen a quadratic, I think I'll do that now. I'm just going to quickly switch on to Desmos. Graphing calculator. All right, so x to the power 4. Is there an easy one? Oh, yeah, x to the power 4 looks a bit like this, right? X to the power 2 looks like this. And all the differences you can see is that x to the power 4 is just steeper, right, at the start. But x to the power 4 can have a lot more wonky shapes. If I add an x, it changes in shape straight away. If I make that x squared, it goes back to being normal. If I make, another x, again, weird. If I make it a 3 and then add x, it becomes even weirder, right? So we can have all sorts of shapes with x to the power 4, whereas with x squared, it's always going to be this same sort of shape. All I'm doing here is shifting that turning point, right? Okay, hopefully that makes sense. I'll also show you guys cubics. So cubics, you can see already it has that weird shape, but sometimes it won't always have that. So if I do plus x, that shape changes. If I do plus x squared, now I have this sort of bumpy shape. I'll see if I can make that larger. So we'll zoom out. Oh, 10 is probably too big. Try 5. You can see, from here, we can tell that this factor here is going to be an x squared term, right? That's sort of like, it's going to be like this term that I was talking about here. I'll just switch back to the PowerPoint. It's going to be like this. And the reason I can tell is because, it goes down and then goes up. All right. Hopefully that makes sense with everyone. And yes. Oh, cool. I think we're back. It's a little bit slow, but I think it dropped out for a little bit. All right. I'm not sure where it dropped out, but yeah. Okay, I'm gonna turn off my camera, just because it did this a little bit yesterday, and I don't want to keep dropping out, in and out. But yeah. Okay, so I'm not sure exactly where we left off, but hopefully it wasn't too long ago where it dropped out. So what I was talking about is the different types of stationary points and where they happen. Um, this one is a cubic stationary point, stationary point of inflection. This is the quartic in its stationary point form, and this one here is the quadratic in its stationary point form. All right, let's switch back to this. All right. Again, I'll give you guys some time to have a go at completing the square, and then we'll try to get into it. Just to recap, um, this is going to give us a turning point, a stationary point of inflection, and a turning point, and that happens at negative b, comma c, right? So just keep in mind if we're doing something like x minus 4 squared plus 5, that's going to become 4 comma 5. All right, have a go at completing the square, and then we'll walk through it. All right, in the meantime, I think I'll check the questions. Yeah, every sack to get a 50 study score. Honestly, this isn't a question I can really answer. It depends. Sometimes yes, sometimes no. I'm not too sure. Um, Again, your exam is worth 60% of your study score. Um, I'm not sure what sort of percentage you'd need to get on your SACs. Like, it changes from school to school. Sometimes, like, schools set really hard SACs, and in which case you might not need to, or you might. I can't give a definite answer on that. I don't know how VCA works. Unfortunately, I would love to know, but yeah, I don't really know myself. I'm really sorry about that one. But yeah. Um, but if you are aiming for a 50, you want to be getting the highest scores that you possibly can. Um, it's really hard to get a 50. Only 30-ish people get a 50 every year. So, yeah, I'm not sure. But if you are aiming for a 50, you do need to give this subject like your all. You need to like definitely like just try your hardest, put in like 100% of your body into this one. Um, but yeah, sorry about that. Um, I think I'll get to this a little bit later. And how would you go about resolving or working on reducing silly mistakes? Well, one of the things I pointed out earlier is doing everything step by step, not skipping algebraic manipulation. Also, throughout the lecture, every time we do a question, I'll point out wherever we can work on reducing silly mistakes, because silly mistakes was a big part of like was a big headache for me in year 12 especially. Not something I noticed too much in year 11, but in year 12 I definitely noticed it. I'm not sure because if the pressure got higher and I started getting stressed a bit more, but yeah, no, I made a lot of silly mistakes in year 12. So we'll definitely talk about that throughout the lecture, because I think it's a very important thing to talk about, and maybe people don't talk about it enough. Okay. All right. We'll get with the lecture. We'll get on with the lecture, and I'll get to these later. But yeah, I think I'll definitely try to answer all of these questions. Okay. Um, all right. So to convert a quadratic into expanded form, we can do the thing completing the square. So hopefully you guys, brainstorm ways we can actually complete the square, or what even completing the square means. Okay. So all we do is we halve this term b. So we're going to halve it, and then we're going to square this new term. And then we add this term to make this perfect square. What I'm talking about when I say a perfect square is x plus a squared. That's what I'm trying to make here. If you guys remember, this gets expanded, so x plus a squared gets expanded into x squared plus 2a times b plus b squared. So that's what I'm trying to do here. I'm trying to make this form here. Okay, so how do I go about making this form? So um, the very first step is to make sure that a isn't really there, and we sort of have to like pull that out, factorize it, maybe get rid of it. Um, Depending what number here. Um, Wait, I just did something wrong. Sorry. You guys probably saw my mistake as well. The b shouldn't have been there. Should have just been 2ax plus b squared. Oh, plus a squared. I was looking at that and I was like, that looks really wrong. Yeah. Anyways, that's another good thing to pick up about silly mistakes. Oh, I just did it again. All right, that's really annoying. That's another thing to pick out about silly mistakes. Every time you write a line of working out, read it again and read it again and read it again to see if it makes sense to you. If it doesn't make sense to you, something has probably gone wrong, and you should probably fix something about that there. Okay, so let's say, we have some term x squared plus bx, right? Let's ignore the c for a bit. And I want to somehow, like factorize this perfectly into a square. How do I even do that, right? I somehow want to I want to try get x plus b squared. That's what I want here, right? Um, how would I? Well, I don't want x plus b squared. I'd rather actually want x plus b over 2 squared. And the reason I'm doing b over 2 is because see this 2a is here. So hypothetically, if this is expanded, I want b in the middle, right? So if b over 2 is times by 2, I'm going to get b. If that's a little bit confusing, just hang on. It might make a little bit more sense later on. Okay, so if I expand this, I'm going to get x squared plus 2 times b over 2, which is going to give me b times x, which is bx, and I'm going to get b over 2 squared. What's b over 2 squared? Well, b to the power 4 divided, oh, sorry, not b to the power 4, b to the power 2 divided by 4. So b squared over 4 here. All right, so that is what a perfect square is there, right? So I'm going to try and make a perfect square from this. So how do I do that? So the first thing is, well, I know, I can take this, so I can take b, I can divide it by 2, and I can square it, right? And we've already done this, but I'll do it again. And that's going to give me b squared divided by 4, right? And now I can add b squared, but just to make sure I don't change the equation entirely, I'm also going to subtract b squared, right? Otherwise, because b squared over 4 minus b squared over 4 is going to be 0. So this equation hasn't changed at all. But if I just added b squared without, subtracting it, well, I'm now dealing with a different equation, and then all of this doesn't actually matter at all. So yeah, subtract it so that the overall expression is the same. And so now this part here is this perfect square here, which is pretty nifty. So now we can just factorize that here. I think it'll do for me, yeah. So now we can just factorize this into this. And then the very last thing you need to do is solve for this term here. So hopefully that makes sense with everyone. I'll get you guys to do a question on this as well. Have a go at doing this. Use the same sort of method that we used. So define your terms. Find what b in this case is. Half b divided by 2. Or yeah, it's the same thing. Divide b by 2 and then square the product and then add it and then subtract it. In this one, I'll give a bit of a hint. Keep in mind the negative term. That's something to be wary of here. So I'll give you guys I'll give you guys 2 minutes to have a go at this one. Maybe 2 minutes is a bit long. I'll give you guys a minute to have a go at this. Okay, I think it's about time. Maybe I'll give you guys a couple more seconds. Sorry, I think my allergies have kicked in today, which is not great, but yeah, going through. Okay, how would we go about doing this? Oh, just skipped over that one. All right. I wonder if I can type. All right, typing apparently is not allowed. All right, so first thing, I want to determine what my b term is. So what I'm going to do is I'm going to split it up so that it looks a lot more like this. So that it looks like x squared plus bx plus c. So what I'm going to do is x squared plus minus 6x plus minus 1. Okay, the next thing to do is to get minus 6, divide it by 2, and then square it. Again, I'm going to do everything in single steps just because it's easier for you guys to follow. And also, it prevents me from making silly mistakes. So this is what I'd actually do on my exam. So negative 6 divided by 2 is going to give me negative 3. And then I'll square this. And from here, I'll get 9. Cool. Um, let's see if that is correct. Pretty sure it is. Looks all right to me. Okay, so now I'm going to add it and I'm going to subtract the term. So I'm going to get x squared minus 6x. Well, I might keep it in the same form, just so we don't get confused. Minus 6x. Sorry about that. That's just pretend this doesn't exist. Pretend that's part of the brackets. Um, plus 9 minus 9 minus 1. Okay, cool. So now what we have here, that is our perfect square. So what we can do is just factorize this, right? So I'm going to get x, so it's going to be in the same form as this, right? So it's going to be x plus negative 6 by 2 squared minus 10, which is going to give me x is equal to minus 3 squared minus 10. All right, who thinks we're done? Well, obviously I can't see, but um, if you think you're done, you'd be wrong. Just because it says plus here, they want it in the form of this. Whenever they ask for a specific form, if it doesn't look exactly like this, they won't give you the marks for it. So what we need to do is we need to somehow change this to a plus. How do we do that? Well, we can. How do we do that? Have a think. We'll let you guys try figure this one out on your own. Okay, so with the plus b bit, it's a bit of a cheesy way to get around it, but you can just throw in a plus here and put brackets around this. And then maybe you can take a negative out to get this. Well, actually, or you can just do the same thing. You can just like cheese it, sort of, show a plus here, put a negative 10 in the brackets. So then c is equal to negative 10, but that plus is still there. It's a bit weird, but this is the sort of things that make VCAR and their, assessors and your teachers a bit happier. Just so, they know that you're paying attention to the detail with that. All right, have a go at this one here. Might be a little bit more tricky. Keep in mind, for us to be able to complete the square, we can't have anything in front of the x. It always needs to be 1. And here it says 3. So think about what you can do about that and how you can get rid of that 3. I'll give you guys about a minute to have a go at this as well. Okay, hopefully you guys are able to have a good go at that. I don't know if it has been a minute yet. Maybe I'll give it a couple more seconds, just in case it wasn't a minute. Let me just see if the stream is still as well. Okay, nice. Um, I'm gonna see if I can get rid of the camera just to make it a little bit better. Um, Actually, not be bothered. All right, let's get into this. All right, how do we go? How do we get around fixing this issue with three? Right? How do we work with this? Well, simple answer: factorize. So, congrats to everyone who found that. All we have to do here is just factorize. So I'm going to pull the 3 out, and we're going to be left with x squared minus 2x minus 1 over 3. Ooh, I guess we'll just have to deal with that. All right, here's a shortcut. I know my final term has to always be in the form x plus b over 2 squared, right? Um, Wait, did I make a mistake earlier? I'm just trying to think. No, actually, it's all good. No, this is fine. Sorry. Okay, so I now know that I can sort of chuck it into that form, but I don't want to do that because it's a really easy way to make silly mistakes. So we're going to still do it step by step. So b, in this case, is going to be equal to negative 2, right? So what I'm going to do is I'm going to half negative 2, and then I'm going to square it. So that's going to give me negative 1 squared, right? And negative 1 squared is just nicely 1. It's pretty neat. Now I can subtract it and add it in, but I can only do that inside the brackets. So x squared minus 2x plus 1 minus 1 over 3 minus 1. Okay, hopefully that's all good so far. But what goes in the brackets is the unsquared version. What goes in the brackets is negative 1, or negative 2 divided by 2, right? We have a look here. It's going to be b over 2 that goes in the brackets. So then we're going to get x minus, but we want it in the form x plus b, right? So x plus minus 1 in brackets. Again, sorry for the really janky brackets, x squared. And then we're going to do minus 1 over 3 minus 1. Again, I'm going to split this up into multiple steps just to prevent making errors. Minus 1 is going to be 3 over 3, right? And this is going to give me x plus minus 1 squared plus, this is going to be minus 4 over 3, right? Because minus 1 minus 3 is going to be minus 4 over 3 plus minus 4 over 3, and we're done. That is now in its completed square form, which is pretty nice. Good stuff to everyone who got that one. That's a little bit more harder than the last one. Okay, so how are other ways we can factorize things, right? This is one way to sort of factorize weird things, right? Sometimes it's hard to factorize things like this, but what are other ways we can factorize stuff? Or solve, sorry, what are other ways we can factorize things or solve quadratic equations? And it's given by the quadratic formula. One question I'd encourage you guys to ask is what or how do we get the quadratic formula? And the answer to that is we get this general term, ax squared plus bx plus c, and then we complete the square on this. So we get this term, and then what we do from here is complete the square. So c, t, s. Have a go with this in your own spare time. It is an interesting exercise, really heavy on algebraic manipulation. But yeah, definitely recommend trying that out. Here's the derivation, so you guys can have a go and then double check it and see how you did here. You can see in this very first step, what they're doing is dividing both sides by a to get rid of that a though, right? You can see that though. Okay, so I'll get you guys to have a go at that, later. But definitely come back and check it out, see if your answer was correct. So the quadratic formula comes from completing the square, like I said. And then after we complete the square, right, we don't just stop here. What we do is we then rearrange and solve for x, right? We subtract this term to the other side, and then we take the square root. Remember when we take square roots in general, we do plus or minuses. You guys will remember when the last time we did a square root was for the distance formula, and you can remember that I didn't do this plus or minus. Does anyone have a guess as to why? Well, take the guess. Obviously, I can't hear you. But the reason that we can't do a plus or minus is because distance is a positive measure. Distance is a magnitude. So it's just like the length of a value, really. Distance is just the length, right? So it doesn't matter. Well, like distance can't be negative. So I'm not going to take the negative side of it. It doesn't make sense. Sorry, I'm just going to quickly grab a tissue. But yeah, it doesn't make sense. So that's why I ignored ignored the negative solution when I took the square root earlier, because it just doesn't work out well. All right, try using the quadratic formula to have a go at this question here. I'll give you guys about a minute or so to have a go at that one. In the meantime, I'll check if the stream is still up. Hey, nice. Also, if the stream does go down at any point, feel free to shoot me an email to make sure I've seen that the stream has gone down, because sometimes I don't see it from my end. I have to go and manually check. Okay, hopefully that was enough time to apply the quadratic formula, play around with it for a bit, and see how it works. I think another thing to note is the quadratic formula isn't on your formula sheet from memory. Could be, but I'm pretty sure it isn't. Ideally, you want to remember every single formula, and obviously this is one of those formulas you will have to remember. But I think you'll use it like a lot, right? It's a formula that you'll end up using a lot. I actually prefer using this formula than factorizing in most cases, just because it's a bit easier for me. All right, so let's try use our quadratic formula. So x is going to be equal to minus b, which is minus times minus 4. So minus 4 plus or minus b squared, which is going to be this again. So minus 4 squared minus 4 times 2 times minus 3. And all of this here is under a square root, divided by 2 times 2. So if you got here, good stuff. You've plugged everything into the formula correctly. Everything it is from now is just a bit of algebraic manipulation, well, not algebraic, just a bit of, crunching numbers, really. Okay, and making sure you don't make any silly mistakes. So the very first step is to multiply the negative in, so we'll get 4. The reason I've done everything like this is so it prevents me from, forgetting about negatives and so on. We'll do plus or minus. What's negative 4 squared? It's going to give me 16, right? And it's going to be minus 8 times minus 3, right? So what's two minuses are going to be multiplied, so it's going to be a positive, and 8 times 3 is going to be 24. in an exam, I'd be talking to myself in my head as I do that, just reminding myself that, that's how maths works. And 2 times 2 is going to give me 4. All right, neat. What is 16 plus 24? The way I like to add numbers like this, because it's pretty prone to making mistakes, is I do 10 plus 6 plus 20 plus 4. And this prevents me from making addition mistakes. So 10 plus 20 is going to give me 30. 4 plus 6 is going to give me 10. So it'll be 30 plus 10, which is going to be equal to 40. Nice. So it's going to be 4 plus or minus square root 40. Well, this square root is simplifiable, right? Because 40 is going to be equal to 4 times 10. So if you guys remember simplifying surds, hopefully that's something you guys remember from your earlier years. 4 times 10 can be broken down into something a little bit simpler. So 4 plus or minus 4 times 10. The square root of this can be pretty easily broken down. I'll get to that in a minute. Sorry, it's very slow writing the mouse pad. That's going to give me, when I take the square root of 4, that'll give me 2, and the square root of 10 is just going to stay as the square root of 10. So it's going to be 2 square root 10 by 4. And I can break this down one step further into, I can split it into 2 fractions. So I'll have 1, because 4 over 4 is going to be 1, plus or minus 2 divided by 4 is 1/2. So that's going to be 10 square root of 10 divided by 2. And that is what x is going to equal. So congrats to everyone who got that. If you left it, if you like just divided by 2 from here, so it'll be 2 plus or minus root 10 over 2, that's perfectly fine as well. You can either split it into 2 fractions or you can leave it in the 1 fraction. Doesn't really matter. I just prefer it like this, so I do it like that. It's personal preference, really. Oh, it's here as well. Let's see if we got it right. Nice. They just didn't simplify it here in this solution. But yeah, the best way to avoid making those tiny errors on a non-calculus test is making sure every single step is written out and every single point of working out is written out. The one part I skipped was I went from -4 times 2 times -3 to 24. I shouldn't have done that. I should have gone -4 times 2, which is -8, written that down, and then multiplied that by -3. I just did it because I got a little bit lazy with writing with the mouse pad. Okay, I'll get you guys to have a go at this one as well. Let's quickly check how long until the break. There's a few. All right, sorry. Just checking if the stream. I'll give you guys a couple more seconds and then we'll go through this. Okay, let's go through this now. Um, all right, so we want to be using the quadratic formula um, and trying to find a way to figure this out using our quadratic formula. So it's going to be the same method that we talked about, here. So the very first step is to plug everything into our quadratic formula, right? So I'm going to do, that's my b term. Really, it should be minus 4 times -1, right, at the front. And that's going to collapse to 4, right, which is nice. This is going to be, again, oh, has there been a mistake that has been made here? Is this the same question? Yeah, it is the same question. Oh my God, I didn't even realize. That's my bad. They got to the same answer. Um, oh, that is on me. I thought that was a different question. Oops. All right, sorry about that. Um, okay, so this is something that we didn't do though. This is graphing that formula. So have a go at graphing it. I'm really sorry about the last slide. I did not realize that was the same question. But yeah, have a go at graphing it and then we'll talk about what it would look like. Alrighty. Um, let's let's get onto this one here. Um, all right. So how do we graph things? How do we graph this? Right. So generally, when we graph things, a few general steps that I always like to tell my students is that one, always draw out after you've drawn out your x and y axes, label your x and y axes, because unfortunately, like Vika will actually deduct marks for not labeling your x and y axes. The next step after making your axes, labeling them, is to find out your x-intercepts, your y-intercepts, your turning points or stationary points. If there are any asymptotes, find asymptotes. If you don't know what an asymptote is, you'll get onto it later on in the year, so don't stress about that. And that's sort of it. After you're done with that, you can sort of move on. After you've sketched your graph, you need to make sure that you've labeled your x-intercept, your y-intercept, and at the end of the graph, you need to make sure that there's arrows labeled at the end to show that it is continuous, if it is continuous. All right, so hopefully you guys got something like this. We have one x-intercept at our negative solution and one at our positive solution. In this case, the turning point hasn't been labeled, but I do recommend that's something that you guys should do. So let's try work out the turning point in this case. With quadratics, it's really nice and easy to work out our turning point. All we do is we take this and we add it to this. So pretty neat there. So we're going to do minus square root 10, and then we divide the end result by 2. So we find the average really between the 2 points, plus 10 square root 10 plus 2 divided by 2. And all of this is going to be divided by 2 again. So that's going to give, all of that's going to cancel out. So this is gone, this is gone. And I'm going to be left with plus 4 over 2 divided by 2, which is going to give me, this is going to crash into 4 over 2. I mean, sorry, 4 over 2 is going to simplify into 2 over 2. well, it's going to simplify into 2, and that's going to be divided by 2. Sorry, don't know what I'm saying. And here we'll get 1 as one of our, that's our x coordinate for our turning point. Next, we need to go and figure out our y coordinates for our turning point. So the way I'll do that is I'm going to do f of 1. So I'm substituting 1 into here. And that's going to give me 2 times 1 squared minus 4 times 1 minus 3. And that's going to give me 2 minus 4 minus 3. Okay. And this is going to be equal to 2 minus 7, which is just going to be minus 5. And this matches up with how the graph is, right? It matches up with these numbers here, and it matches up with that. So that's going to be 1 comma negative 5. And since this graph is continuous, what I like to do at the end is just throw in these little arrows that show it is continuous. If it's not continuous, keep in mind that a closed circle like this, a colored in circle, that represents inclusive, and an open circle like this represents non-inclusive. So hopefully that makes sense. Alrighty, so let's just look at the quadratic formula and talk about this thing called the discriminant. Maybe it's something you guys have heard about before. It's a pretty useful property that that we can use a lot in problem solving. And yeah, so let's get into it. So we can see that this term here, the b squared minus 4ac term, can't be negative just because we can't have negative numbers in square roots. If you guys are doing specialists, you will cover complex numbers at some point. And complex numbers, interestingly, are numbers that have a negative square root. So, it's like 5 plus the square root of negative 5. It's things like that. That's a complex number, but that's not going to be covered in methods. And so in methods, we only talk about real numbers, and real numbers are when you like take the square root of a positive number. That's a real number, really. So yeah, so b squared minus 4ac needs to be greater than 0. So because of the plus or minus, we're given two options if the b squared minus 4ac term isn't 0, right? And so now this is known as a discriminant. And it generally has a symbol of this triangle thing here. So when our discriminant is equal to 0, there will be only one solution because that plus or minus isn't there. So like imagine if this part of the graph isn't there, right? It's just going to be plus or minus 0, right? So then our only x solution is minus b divided by 2a. But pretending that this is there, now we have plus or minus, so we can plus this or we can subtract it, so we'll get two solutions. If the discriminant is less than 0, well, we can't compute this in the real numbers, right? There is no real solution. So that for that we say, so no real solution. So no real solution. And so that means there are no x-intercepts. No x-intercepts. Pretty nifty. But yeah, that's that. So hopefully that makes sense. We can use it a lot in a variety of different types of problem solving, especially in year 12. So this is something you should definitely hang on to. Same with the quadratic formula and same with everything we've talked about so far, you need to hang on to when you get into year 12 as well. All right, so what does this look like graphically, right? So if we have no solutions, it's just not going to touch the x-axis. If it has one solution, it'll touch the x-axis once, and that generally means that there's a turning point though. And if it has two solutions, well, then it'll look like a normal quadratic with the two solutions there. This is x squared. This term here, this is just y is equal to x squared, right? If we try work out the discriminant for this, our discriminant is going to be b squared minus 4ac. This doesn't have a b squared term or a 4ac term, so it's just going to be 0. And so that matches up with what we see. All right, have a go at this. This is a pretty cool application question, I think, or a problem solving question. sorry. But yeah, have a go, and I'll give you guys a couple minutes to do that. In the meantime, I'll just check if the stream is still. Okay, hopefully that was enough time to have a go at doing this question. And hopefully you guys got the solution. All right, so find the values of m for which the graph of y is equal to f of x has exactly one x-intercept. Okay, so what sort of things are we looking for, right? One of the things we're definitely looking for here is a discriminant of the value of 0, right? So we want our discriminant to equal 0 here, right? Because that's what tells us when it has one solution, discriminant of 0. Okay, so let's create our discriminant equation here. So this is our b term, this is our c term, and our a term in this case is going to be 1. So we'll get m squared, so b squared, minus 4 times a, 4, sorry, times a, which is 1, times c, which is 4. Okay, cool. And we can equate this to 0. Well, for now, we'll just say this is our discriminant. And now our discriminant is going to be equal to m squared minus 16, right? And now we can equate this to 0. And we'll get m squared minus 16 is 0. And now solving for this gives us m squared is equal to 16. And from here, m is equal to plus or minus 4. Cool. One thing that like sort of hints that we'll need multiple solutions for m is that it says find the values, like plural s, values for m of m, for which the graph y is equal to f of x has exactly one x-intercept. So m can equal 4 or m can equal -4. Also, I did skip a step here. Like, how did I go from here to here? All I did was I took a square root. So did m is equal to plus or minus the square root of 16. All right, hopefully that is all good. All right, let's talk a little bit about transformations. So there are three main types of transformations. We have reflections, where we get something like this and we flip it in the plane so that it ends up like that. We have dilations, which stretch and squeeze. Another dilation might have been something like this. And we have translations, where we just shift our graph around. We move it from this point. We can move it upwards, or we can move it sideways. All right. So here are some types of transformations. So we can have dilations in the x-axis or dilations in the y-axis, and that changes what the meaning is, right? Sorry. A dilation by factor of a from the y-axis affects our x values, right? What I like to think about is we're dilating it from the x-axis, right? We're moving it away from the x-axis or moving it towards the y-axis, not away from the x-axis. We're moving it away from the y-axis or towards the y-axis, right? So all we're doing here is really affecting our x values. Other words that we can, or other ways we can say that is dilation by a factor of a in the direction of the x-axis. A dilation by factor b from the x-axis is, changing the distance from the y values, or changing the distance from the graph from x, right? So this affects our x values. So from x affects y values, and from y affects x values. Another thing to note is a reflection in the y-axis affects x values, sorry. So, if we have a graph like this and we reflect it in the y-axis, we'll end up with a graph here. So, our x values have changed. If we reflect it in the x-axis, you can see here that the y values have changed, but the x values have stayed the same. Translations in the positive and negative direction only affects y values. So translation in y affects y, translation in x affects x. So, if I'm translating this graph up in the y-axis, it'll look like that. Down in the y-axis, we'll look at this. In the x-axis, we'll be moving it from side to side. Okay, have a go at answering this. And I'll go through the solution. Do this, you should always be done in this order. And again, why, right? Like, don't take my word for it. We saw why that happens, right? So if the dilations, you can have a read of that yourself. But whenever we apply a dilation or reflection, that translation is going to be shifted. So that's really it. All right. So there's a couple ways of actually figuring out our dilations, reflections, translations, and that jazz. One of the ways is via the coordinate method. So the coordinate method is when we apply these transformations to certain coordinates, and then we sort of map it out, and then we flip it back to in the normal coordinates. So we sub it into the equation. That probably won't make sense until we do an example, but yeah. So it takes longer and has a lot less room for errors. I use this method a lot, just because I found it a bit easier for me to visualize things. But yeah. Okay, so first we apply our dilation from the y-axis. Again, that's a change in x, so we apply it to the x. A dilation in a dilation from the x-axis, and so we apply that to y, right? A reflection in x, so our y-axis will change, and a reflection in y, so we apply a negative to both, and a translation in c up and d right. Right is always going to be left because on our right, wait, that does not make sense. Sorry, I don't know what I said. Right is always going to be positive because on our um, sorry, let me just draw this out. Um, on our Cartesian plane, the right side is going to be positive and the left side is negative, right? And up is positive and down is negative. So whenever you see a translation in C up, you're going to plus C. And whenever you see something to the right, you're going to do plus D. If it's to the left, then you do minus. But yeah, that's important to keep in mind. I should probably get rid of this before it covers the other working out. All right. So next, we create this new variable called x prime, and we equate it to this new x coordinate. And then we also do the same for y. Okay, after we do this, we can now substitute this and resolve for our normal x values. So we do x, we equate this and then we resolve for x, and then we now substitute this into our original equations. So this is the substitution we make into y, and this is the substitution we've made into x here. So hopefully that makes sense. It's a bit finicky because there's so many things that can go wrong here, and then even when you substitute it in and solving for everything, that can also make it go further wrong, or make it stuffed up a little bit more. Okay, so hopefully that makes sense. The other way of doing it is known as the replacement method. The reason I didn't like this one is because it requires a lot more memorization, and I don't memorizing things that much. Um, and it's sort of derived from this. It's derived from this, but you just instead of um, having to do everything manually, you just memorize all of these. So you memorize that a dilation from the y is going to change the x, but it's going to be 1 over a. So whenever you see a dilation from, or dilation a from y-axis, you'll have to apply like 1 over a to x. And that's because here you can see that it's 1 over a when it gets applied to x. So it's a bit strange like that. Um, the reflection in the x is still the same, and reflection in the y is still the same. When we change y, or when we dilate from b, that doesn't change the, we don't have to reciprocate the a, or find the reciprocal. And whenever we, go right, we have to put a negative. Whenever we go left, we put a positive instead. But that doesn't change anything for y. So it's just like flipping everything for x, really. Since when you're going right, you're going, minusing d. When you're dilating a from the y-axis, you're dividing it by a instead of multiplying it by a. Just things like that. But that's why I didn't really like the method, because I thought it was quite prone to error. So I didn't use it as much. I just try to get really fast with the coordinate method. But eventually, if you do the coordinate method enough, you'll just end up memorizing it anyways. So yeah, practice, just practice, 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 really. All right, I'll let you guys have a go at this. I'll give you guys a couple minutes to have a go at this one here, and then we'll move on. I'll just quickly check if the stream is still up. Yeah, it is. Nice. Alrighty, let's go through this question here. So a function f of x is equal to 1 over x undergoes the following transformations. A reflection in the x-axis, translation 1 up, and 1/2 right. Okay, using the replacement method, state the transformed function g of x in the form minus a divided by bx plus c plus d, where a, b, c, and d are integers. Okay, cool. All right, so the very first thing to note is all of this. We sort of need to have this on the forefront of our minds. So dilation from y, so that means I'm going to apply it to, I'm going to apply 1 over half to x, and 6 from x. So I'm going to do 6 times f of x, and I'm going to just, with f of x, I'm going to do x over 2. They say reflection in the x-axis. Whenever reflection happens in the x-axis, it's applied to y. So I'm going to chuck a negative in the front. Translation 1 up and 1/2 right. Okay, so keep in mind that that is applied on top, right? Because you can see d right, and it was applied very last, and it's still divided by a. So we need to keep that in mind when we do this. So it's going to be x minus 1 over 2. You can't really see that though, but imagine that's a negative 1 over 2 though. And since it's right, I'm going to be subtracting, and translation 1 up. So I'm going to do plus 1. All right, so the last thing I need to do is just plug everything in. So it's going to be minus 6 times, when I substitute everything into here, it's going to be, well, actually, I think the very first step I should probably do is substitute everything into x first. So it's going to be 1 over x minus 1/2 divided by 2. And that is going to give me, so right now I have x minus 1/2 divided by 1 over 2, which is just going to become 2 over x minus 1/2. Just because I'm running out of space, I'm going to shorten out my working out. So it's going to be 2 over 2x minus 1 by 2. And I can simplify that to 4 over 2x minus 1. Sorry, there should be a division here, not a subtraction. Okay, cool. So now I've applied all my x transformations. I just need to apply my y ones, right? So I can just put that into here. For 2x minus 1 plus 1. So minus 6 times 4 is going to give me negative 24 over 2x minus 1 plus 1. And I want to leave it in the form of this, right? So I want minus 24 over 2x plus negative 1 plus d. Okay, cool. So that here is our final answer. Sorry, that was very janky. Oh, I left out the negative. There should be a negative in the front though. My bad. Yeah, sorry about the really messy handwriting, but hopefully that makes sense. Hopefully I haven't made any mistakes here either. Feel free to shoot me an email if I have, and I'll try correct it. Just in the interest of time, I'm not going to spend too much time just sticking around and trying to like double check and triple check if I've made any mistakes. Ideally, in an exam, what I would do is after I do all of this, or after I do every single step, I'd double and triple check just to see if I've got it right. And only then would I move on. But you know,
just because in the interest of time, I'm just going to move on to the break so then, you guys can kind of relax and chill.